In this video, I'm going to talk about work and energy. So, what is work? Well, work is something that is done by forces. So we say that forces, when they act on an object, they do work on that object, and they do it to change the object's energy. So if you remember from Newton's laws, forces accelerate objects. And when an object accelerates, it has more energy because now it's moving faster. So forces, when they act on objects, they change the energy or do work. So if the force is constant, so if force is constant, so the work done by a constant force, we'll call work capital W, is equal to that force times the displacement, but only the component of the force that is parallel to the displacement is going to do any work. Okay, so in this case, we put a little subscript of parallel lines to indicate that the force must be parallel to the displacement to do work. Okay, and then here we're indicating the displacement with the variable s. Okay, now work, we said the work done by a force is done to change an object's energy, so the units of work are the same as units of energy, which are called joules, okay, or capital J. Okay, so this is also a unit of energy. So you could think of work, it's kind of like energy in a way, but specifically work is done by a force to change energy. Okay, so we may also write the force in this way, or the work done by a force in this way. The work is equal to the force times, sometimes displacement is given with a d, so I'm going to write it with d2 just in case you see it both ways, times the cosine of the angle theta, and this angle is the angle between the force F and the displacement d. So you may see it written either way. Some people use S for displacement, some people use D. And anytime you see a formula like this, where it's two things multiplied together times cosine or sine of some angle, that angle tends to be the angle between the two variables in front of it. Okay, so we may draw a force to the right, maybe it's pushing an object, and the displacement is also to the right. So in this case, our angle would be 0. The force could also be to the left, and the displacement could be to the right. So we've seen that in cases of friction. Something may be moving to the right, but friction is acting in the opposite direction to slow it down. So in this case, theta would equal 180. And then you could also have forces that are acting at some other angle somewhere between 0 and 180. And so only a component of that force would be actually in the direction of the displacement. And that's why we use this cosine of theta, is it pulls out the parallel component for us, and so we don't have to worry about it. So really, if you just use this expression for the work, as long as you're able to find the angle between your force and your displacement, this will get you the work done by the force really easily. So just to show you what I mean, force times the displacement times the cosine of the angle between them. If you have some force acting at some angle, and maybe you have some displacement, I'll draw this in another color, okay, because these are not the same type of vector. Displacement and force are two different types of vectors, so you can't just add them together and do vector operations such as addition and subtraction with these vectors. But this force vector can be broken into components that are perpendicular. So I'll call this F perpendicular. So this is typically the symbol for perpendicular. And then it can also have a component that is parallel. So this is F parallel to D. And only this component of the force, so only the parallel component, is actually going to have any part in moving this object through this displacement. So parallel component does work. Okay. So another way to say this is that if it's moving to the right, its velocity or its energy is kind of increasing because it's moving to the right. So any component of this force that's trying to push it up or down or perpendicular, it really isn't doing anything because it's not making it actually speed up in the positive y direction or the negative y direction the way I've drawn it. Okay, so it's only going to be able to speed up or change its energy in the direction of its displacement. So only the force that's parallel to this displacement can do any work. Okay, so let's do some more simple examples. Say we have an object and we drop it. So it's going to start up at the top and drop down some distance. So it's going to go down. Maybe I can draw that better. It's going to go down some distance, d. And the force pulling this object down is going to be its weight. Okay, so if we were to calculate the work done on this object would be the force acting on it, which this case is the weight, so little w, times the displacement times cosine of the angle between them. But since they're in the same direction, that angle is just going to be 0. So this is just going to be the weight, or mg, times the displacement. Okay, so the work done is positive. Now, if we take this object, but this time we throw it up, so it's moving up, its displacement is now maybe the same, but now it's going in the positive y direction. The weight is still going to be down. Okay, so it's moving up, but the weight is going to be down, the displacement is up. So now the work, let me do this in blue, the work done by the weight is going to be the weight times the displacement times the cosine, but now this angle is going to be 180, okay, where here theta was just 0. And so cosine of 180 is minus 1, so this is going to be minus mg times the displacement. So what this means is the work can be positive or negative. It's going to be positive or so this means that your work may be positive or negative, and it really depends on the direction of your force relative to the displacement. So let's look at some properties of work. Work, first off, do this in another color. Work is a scalar. Okay, so it is not a vector. It doesn't have a direction, and it is not a vector. So we said the work is equal to the force times the displacement, and only the parallel component of the force actually does work. Okay, so if this is our equation for the work, then this means that if d is 0, displacement is 0, that means the work is also 0. So this work wasn't able to change the energy of the object it was acting on because it wasn't able to move, right? It didn't displace, it's not going faster than it was before because it didn't move. So the work done is 0. Okay, so it has to be able to go through some displacement. Okay, another property, if the force is perpendicular to the displacement, okay, so these are vectors. If the force is perpendicular to the displacement, then the work is also zero. Okay, the work done by that force is zero. And then we saw previously that the work can be positive or negative, so the work is less than zero or negative. This means that energy is removed from the system. So this is kind of like when friction is in the opposite direction of the displacement. It's taking energy away. Okay, and it's causing the object to slow down. If the work is positive or greater than zero, this means energy is added. Okay, so this means you're pushing in the same direction that the object is moving, and so it's probably, if there's only one force, it's accelerating or increasing in energy. So positive work means you're adding energy to the system. Okay, and so this occurs, you add when F and D are in the same direction, and you remove energy when, put this down here, when F and D are opposite directions. Okay, much like friction. Let's look at a quick example problem to get an idea. So we have some object, and it's going to be moving to the right, but it's going to be moving because of some force that's at an angle. So we have a 300 Newton force, and it's going to make an angle of 30 degrees with the horizontal. So this is kind of like you're pulling a suitcase at some angle, but it's only moving horizontally across the floor, even though you're pulling at some angle. Okay, and it's going to move to some distance. Maybe I'll draw it the right size. Okay, so it's going to move, and we're still going to be pulling on it up and to the right. And it's going to move a distance of 20 meters. Okay, so our force is 300 newtons. Our displacement is going to be a positive 20 meters. And the angle between our force and the displacement is 30 degrees. So if we look at our equation for the work, it's going to be the force times the displacement times the cosine of the angle theta between the force and the displacement. So we can plug in, this is 300 newtons for our force times a 20 meter displacement times cosine of 30 degrees. If we do this, we get 5,200 joules, or 5.2 kilojoules. So it's often, we get pretty big numbers for joules, units of work or energy. Joules is a small unit of energy, and it's positive. So this is how much energy we added to the system or to the block. So in this case, the block is, or this object is just our whole system. And this is how much energy we added by pulling on it, accelerating it through this distance. Okay, so if this was frictionless, now this object would be moving faster without friction. Okay, and so that's the sense that we mean that we added energy to the system. We mean that in the absence of friction, if this is the only force, it would make this object speed up as we pushed on it through this displacement. Just talk about this a little bit more. So you have this object at some time t1, and later at some time 2, it's been pushed to the right by some force. And it's been moved through some displacement d. Okay, so just to reiterate, Newton says applying a force will accelerate an object. Okay, so this means that the work from force F, so I want to make sure to make this as a capital W, not to be confused with the weight. The work done from a force F will increase if it's in the same direction, increases the energy, so it's going faster. Okay, but on Earth, the box would stop, right? On most surfaces, if we push something, we apply some force, and this object moves, it's going to stop. And so why is that? If applying a force does work in an object, and we say that's going to increase the energy or accelerate it, why does it stop? Well, it's because this is not the only force that is acting. Most of our experience tells us the object is going to stop, but that's because we can't escape the fact that there is friction. So when objects slide across surfaces, there is always friction, typically, that's going to slow it down. So we do have this force that's in the same direction as the displacement. Okay, and so this adds energy to the system. But we also have friction that's acting in the opposite direction of the displacement. And so at the same time as this object's moving, it may have energy that is removed. So friction removes energy from the system. Okay, and so even though it's moved through this displacement and it stops, it's not moving, its energy hasn't been increased. So this tells us that the net work or the total work is going to be zero. Okay, and so this looks like no energy has been added. Okay, but in reality, our pushing force added energy to the system, but at the same time we had friction removing energy. So there was a positive work done by this force and a negative work done by this force, and they kind of canceled each other. If we have a constant net force, so write F net, this means that there's going to be a constant acceleration. So we've been looking at the work done by constant forces. So a constant net force will lead to a constant acceleration. So that means we can look at our constant acceleration or kinematic equations. So we can look at this one, the final velocity squared is equal to the initial velocity squared plus the twice the acceleration times the displacement. Okay, so this would normally be delta x or delta y. And so if we solve for the acceleration, we get the final velocity squared minus the initial velocity squared, all divided by 2 times the displacement. So now if we look at Newton's second law, it says that F net, the net force on an object, is going to produce an acceleration, so mass times acceleration. So now we can plug this in for acceleration. So we get Vf squared minus Vi squared over 2 times the displacement. Okay, so if we take this and we multiply by the displacement on both sides, it's going to cancel on this side, and what we're left with is F net times the displacement is equal to, I'm going to separate these terms, 1/2 mvf squared minus 1/2 mvi squared. Well, this is a force times a displacement. And not only is that, it's the net force. So if we added up all the forces, this would be the net force times the displacement. So not only is this the work, this is going to be the total work done on an object. And it looks like it's the difference in some quantity. And we said that the work done by a force changes the energy, and this looks like some energy has changed, or some quantity has changed. So we're going to call this, so this is some difference or change in some quantity. And so it makes sense for us to define this as the energy. And so this is going to be our net work or total work. And we're going to call 1/2 mv squared our kinetic energy. So this is our final kinetic energy minus our initial kinetic energy, or delta K, okay, where kinetic energy is 1/2 mv squared. Okay, and so this is what we'll call kinetic energy. It also has units of joules, since it's equal to, the change in kinetic energy is equal to the work. And this is the energy we associate with motion. So kinetic energy is the energy of motion. Delete this. Okay. And it has units, just like work, of joules. So this is known as the work energy theorem. Okay, and you can, assuming constant forces, you can derive it using Newton's second law and kinematics very easily, as we just did. So work energy theorem. And this says the net work or total work, okay, or work total, so not just the work done by one force, but the total force, is equal to change in kinetic energy. Okay, so if you only looked at one force, that might not equal the change in kinetic energy, because we saw when we pushed our box with friction present, if it stops, it's not going any faster than it did before. It doesn't have any more kinetic energy. Okay, but then when we factored in friction, we saw that it took out just as much energy as we put in, and so the kinetic energy was 0. Okay, so if we look at this, if the kinetic energy, K, capital K, doesn't change, so the object has the same velocity before and after, this means that the net work done by any forces acting on it is 0. We can also go the other way. If the total work or the net work is 0, that must mean that the kinetic energy is constant or not changing. So not changing. Okay. Now K, kinetic energy, is always positive. Okay. But the work, as we've seen, the work and delta K may be negative. So we may start at some higher velocity and slow down, and so our change in kinetic energy may be negative, meaning it decreased. So work may be negative if K decreases. Okay. But K itself is always positive, and that's because if we look at our definition of K, 1/2 mv squared, mass is always going to be positive, and even if our velocity is negative, it's going to get squared, so that means everything on the right is positive, so the kinetic energy on the left must also be positive. So let's look at another example. So we have a block, we're going to drop it, mass equals, say, 10 kilograms. It's going to accelerate downwards because of the weight. So the weight is a force that's acting on this mass. And the initial velocity is going to be 5 meters per second. Okay. And then after some time later, it's going to be down here. And now it's going 10 meters per second. So we notice the velocity has changed. Well, that means that there must have been some total work done on this object. So in this case, there's only one force doing work. That work is going to equal the change in kinetic energy by the work energy theorem, or K final minus K initial. Final kinetic energy will be 1/2 mvf squared, which is 1/2 m, or 1/2 times 10 kilograms times it's going 10 meters per second at the end squared. This will give you 500 joules. The initial kinetic energy is 1/2 mvi squared, or 1/2, again 10 kilograms, but now 5 meters per second squared, or 125 joules. Okay, so the work is Kf minus Ki, or 500 joules minus 125 joules, or 375 joules. So this is the work done by the weight, or by gravity, in accelerating this object or moving it through some displacement. Okay, and one thing that you notice is that we doubled the speed, but the energy more than doubled, because the kinetic energy goes like v squared and not just proportional to the velocity. Okay, so now let's look at another type of energy. So you've probably heard of potential energy. And potential energy is just another word for stored energy. Okay, so we said that doing work, a force doing work on an object changes the energy. Potential energy is energy that is stored that has the potential to do work. Okay, so it has the potential to speed up an object or move it through some displacement. So the first type of potential energy we're going to look at is gravitational. So gravitational potential energy. So if we were to take an object and move it up, okay, so its displacement is up, and actually we're going to call this the height, h. Okay, so we throw it up, it goes through some height, the weight is acting down. So the work done by gravity in this case is the force times the displacement, and they're in opposite directions, so it's going to be minus mg for the weight times the height. Okay, so this says that the work removed energy from the system because it's negative, and that amount of energy is equal to mgh. So the question is, where did the energy go? So imagine we throw it up and it stops after going some distance h. So now, so it's at the top, it's at its maximum height, okay, when it's up here. Okay, so if we take this object and just look at it from the top, the moment after it's at the top, it's going to start going down. Okay, so now we can look at it on the other side. The work is now going, or the weight is still going down, but now it's in the same direction as this displacement. So if we calculate the work now, it's still going to equal mgh, but it's going to be a positive mgh. So now gravity has done positive work on the object. Okay, so where did this energy go? Well, it was stored when it was in the top. It was stored, and if the object is released at the top, okay, or nothing is holding it back, then gravity will add this energy back to the block. Okay, so we say that when an object is up in the air, it has some gravitational potential energy, and then when it starts to go down, that's gravity doing positive work on the object, or accelerating it, speeding it up, or increasing its energy as it comes toward the ground. Okay, so we define the potential energy. So sometimes this is called, PE is used for potential energy. Some people use KE for kinetic energy. I'm going, and I'll do a subscript G for gravity. I like to use U, so U is also used for potential energy of gravity, is equal to the mass times gravity times the change in the height. Okay? And since doing negative work, so when we did negative work, we increased the potential energy. Okay? So if MGH, if this is the potential energy, then when we did negative work against it, raising it up, that's what increased the potential energy that gravity then had to pull it back down. So the work done on an object is equal to the minus the change in potential energy. If we look at our two definitions for work in terms of energy, we have the work is equal to minus the change in potential energy, and we have the work is equal to positive change in kinetic energy. Okay, so that means we can set these things equal to each other. So that means we can write delta K is equal to minus delta U. So then we can expand this out and we get Kf minus Ki is equal to minus Uf minus Ui. Okay. And now if I distribute this minus sign, get minus Uf plus Ui. And I want to move my final quantities over to the same side and get my initial quantities on the same side. And if I do this, I get Kf plus Uf equals positive Ki plus Ui. Okay. Well, if I call this looks like my total energy. It's my final kinetic plus my final initial energy. So this is going to be my total final energy. And this is going to be my total initial energy. Okay. And so what it looks like is the energy that I had at the end is equal to the total energy I have in the beginning. And so it didn't change. And so this means that your energy is constant. So your total energy is constant, or you may have seen the word conserved. So this is a statement of conservation of energy. Okay, and it just means that our total final energy is equal to the amount of energy that we started with. So now let's look at another type of potential energy. We're only going to look at two, and it's called elastic potential energy. So we had gravitational potential energy and now elastic potential energy. And so the object that you think of when you think of elastic potential energy is a spring. So the force of a spring changes as it is displaced. Okay, so a spring force, F spring, is equal to K, little k, spring constant, don't need to get that confused, times the displacement delta L, or sometimes in some textbooks you see F spring as written as minus Kx, where x is your displacement instead of delta L. And if you use this first expression, you kind of just put in the direction by hand. In the second expression, this minus sign tells you that the force is in the opposite direction of the displacement. Okay? But in either case, the force changes with displacement. So if we wanted to find the work done by a spring force, which is not constant because it depends on how much it's stretched. If you stretch a spring and then release it, as it moves, the force is going to change at every point because it's displaced some different amount. So, to find the work done by a spring, or a variable force by a variable force, such as a spring, we can use the average force from 0 to kx. So what do I mean? Well, if we plot the force times the displacement, so F or spring times x, when x equals 0, the force is just 0, but then it increases as we stretch the spring. Okay, and it's linear. This looks like the equation of a line. Okay, so this is my spring force. So when it's some distance x away, then the spring force, its magnitude is just kx. Okay, so what we can do is we can just take the average of this force. Okay, so F average of the spring is kx over 2, so it's just halfway in the middle. Okay, so the average is just half the total force, kx, since it's linear. So you take final minus initial divided by 2. Or actually your average you add. You take your initial point 0 plus your final point kx and divide by 2. Okay, so that's just the definition of an average. And then the work is done by this average force times the displacement x is equal to kx over 2 times the displacement x. And so this is just equal to 1/2 kx squared. Okay? So for the potential energy of a spring, it's going to equal the work done. So this force is negative, so it should be negative. And so the potential energy of a spring, sometimes this is called elastic potential energy. So we'll put U sub elastic. And this is equal to 1/2 kx squared. Okay? So now if we want to write the total energy, we have to include all types of potential energy. So this is kinetic plus potential. But our potential might be gravitational or elastic or both. Okay. So now if we look at conservation. So now if we look at conservation of energy, we have our final total energy equal to our initial total energy. Okay. And these potential energies, both of our potential energies, come from what are called conservative forces. So these come from conservative forces. Okay, so we had potential energy of gravity is equal to mgh. We had elastic potential energy, or potential energy of a spring, equal to 1/2 kx squared. Okay, and so both of these, if you look, both of these types of potential energies depend on displacement. Okay, so they depend on your location, or how much your location has changed. Okay, and so we say that the work done by conservative forces or conservative forces have associated potential energies that depend on position. Okay, so non-conservative forces, an example of a non-conservative force would be friction. So non-conservative forces like friction do not have potential energies. So do not have potential energies because friction doesn't depend on your position. Okay. And so non-conservative forces are sometimes called dissipative because they may cause energy to be dissipated from the system instead of stored, where potential energies, they can store energy depending on where they are. So if you're higher up in a gravitational field, you can store potential energy. If your spring is compressed or stretched more, so X is bigger, you can store more energy in the spring. But non-conservative forces like friction, if you move them through a displacement, that energy gets dissipated as heat and it's not able to be stored. So they're called dissipative or non-conservative forces. Mechanical energy may not be conserved. Okay, so non-conservative forces like friction, so non-conservative forces will do work to remove energy. Okay, from the system. So you have your initial kinetic and potential energy, and that's going to be equal to your final kinetic energy plus your final potential energy minus however much energy or work was done by these non-conservative forces that was removed. So you started with some total mechanical energy. Okay, so mechanical energy is what we mean by kinetic plus potential. And then at the end, you still had some final mechanical energy. So I guess this should read starting total mechanical energy. But at the end, you have this final mechanical energy, but maybe you've lost a little bit. So this is energy that is lost or removed. It's really not lost. It's lost from the system, but it's lost or moved to friction or by friction and other non-conservative forces. Okay, so I will say, just to be clear, total energy is always conserved. So this energy that's lost to heat or friction, it went somewhere. So it went to heating up other things that are outside of the system. But it's no longer mechanical energy that we can use. So it went somewhere. It's still conserved. It's still there. But the energy in the system is not conserved. Okay, so the energy left the system. It is no longer there. Okay, so energy always goes somewhere, and it is conserved in totality. If you were to look at everything and every bit of energy in the universe, but for a given system, if there's any non-conservative forces doing work, such as friction, then that energy gets removed and gets turned into a form that we can no longer use anymore, and is not considered mechanical energy. I think it's important to pay attention to some terminology. So energy can be either transferred or transformed. So what's the difference? So an object's energy or a system's energy objects or systems. Your system may be one object or multiple objects, may be transformed. Okay, the key word is formed from one form to another. So an example would be from kinetic energy to potential energy, or vice versa. So this is an example such as with gravity. We throw an object up and we give it some kinetic energy. It's going to take, gravity's going to take that energy and start to store it. And then on its way down, gravity will do work and turn that potential energy into kinetic energy, and it's going to speed up again. Okay? And then energy may also be, I guess maybe transferred to another object, or system. Okay, so you may transfer object and give it to another object or another system. And so this is what we mean by transferred. It moves to something else. It may not necessarily have been changed to a different form. Likely it has. But I may have one object that has kinetic energy, and it bumps in and collides with another object and gives that other object kinetic energy. And so that second object takes energy away from the first object, and we say that energy has been transferred. The rate at which we transfer energy, or the rate at which we do work, is called power. So this is how fast work is done. So work is done, or energy is transferred. Okay, so if we look at our definition, that means power is going to be the work over, work over some amount of time. So the units are going to be watts. And if we look at this equation, work per time, that means a watt must be, let me write it like this, 1 watt, capital W, is 1 joule per second. Okay, so we abbreviate watts with a capital W. Capital W as a unit will be watts, and as a quantity would be work. So don't get these confused. So this is work per time, or we know work is just a change in energy. So it's a change in energy over change in time. Okay, if time equals 0, if our initial time is just time equals 0, then delta t and t are the same thing. Okay, so this tells us that our energy, our change in energy, is just our power times however much time that energy is being transferred. Okay, so we can look at this unit. Power is in units of watts, or it may be in units of kilowatts. And then time is typically seconds, but if we use a time of hours, then energy looks like it has units of kilowatt hours. And so this happens to be the unit of energy that your electric bill is in. So the power company will tell you how many kilowatts of energy, kilowatt hours of energy they will tell you how many kilowatt hours of energy you used, and then they will charge you per kilowatt hour some rate. Okay, and so we'll look at some example problems and show you that a kilowatt hour is exactly a unit of energy. We can get another equation for power. Our power is work per time, or energy per time. And the work done by a force is the force times some displacement, and it has to be the parallel component of that force. Okay, so we can take that divided by time. But then displacement over time, that's just velocity. So power can also be expressed as the component of the force that's parallel to the velocity. Okay, so force times velocity. And then this has to be parallel, so you could write F v cosine theta. And so this looks similar to the work equals F parallel to D, or F d cosine theta. Okay, but if you replace D with velocity, then your work becomes your power. Okay, so this may be another way of finding power if you're given the velocity. Okay, and then again, if your angle, if theta is just 0 degrees, so your force is in the same direction as your velocity, then your power becomes just the force times that velocity. Okay, so in another video, we're going to go through work. So in another video, we're going to go through work, kinetic energy, potential energy. We'll do some problems with conservation of energy and power, and let you see some examples of how all of these equations are used and how we can use some of these concepts to solve problems.